Alright, so welcome back. Today we're talking about Dalton's law, and Dalton's law is the last of the gas laws. So that's some really good news. And Dalton's law, when it comes down to it, answers the question, how do mixtures of gases behave when you put them in the same container? So far everything we've studied has either been gases that leave a container, or an individual gas in a container. But we've never said what happens when you put multiple gases in the same container, which is the most common scenario, right? So Dalton's law is going to help us answer this question today. Ultimately, all we're doing is actually just Puvner. This, honest to God, already answers this question. But the question comes down to how do we deal with the N here, right? That's really what today is about. So really quickly, what does that N stand for again? Right, so again, pressure in atmospheres, and volume in liters, and temperature in Kelvin, and R never changes. What number is that again? Alright, so we're going to be using Puvner again today. There is one consideration to take into account here, and that is the gases are non-reacting. Non-reacting here means not that they can't react with anything, just that they don't react with each other. Otherwise, something like this happens. So this is going to be the reaction between acetylene and oxygen. Both are common gases in like field welding work. So commonly stored in the back of vans. And that would be really hard to measure, right? And so our gases can't react with each other. All right, if our gases can't react with each other, we're basically saying we have two different gases sharing the same space, right? That's really the consideration we're trying to have right now. And so if that is the case, then we can come back to our friend Puvner for a second and say, well, what are we trying to find? Or put another way, what's not changing? And I would argue that we're dealing with what's called a shared container, right? And in a shared container, these three things aren't going to change. Your volume, your temperature, and your R. In other words, if they're in the same jar, the same balloon, the same pressure vessel, I don't care what you're talking about, it's not like the walls are suddenly going to change, right? The container is the container. So that's off limits. And R is not going to change, it's a constant. And T, if it's in the same container, the whole container is at the same temperature, right? Which really just leaves us P and N to be related. And that's going to make our life a lot easier because obviously our pressures and our moles are where this law has to come from. Our V, R, and T, because they're being shared, don't matter. So, a quick question. We need to make one more definition before we go on, and that is that of partial pressure. Now, partial pressure sounds like what it is. It is a pressure coming from one thing out of the group. The pressure by any single species in a mixture in a shared container. We said a shared container is the same wall, same temperature, and all that. So we're really looking at just the pressure and the moles of any given species, of any given chemical. And these partial pressures are going to be the name of the game today. So they are part of the whole picture. And if you add up those parts, then you get the total. That's Dalton's law. And it's close to a common sense law. If you add up all the small pieces, you get the big thing. If you add up each student in a classroom, you get the class, right? Okay, so which number will be bigger in a mixture of at least two gases? Now this is a pretty long definition, right? So I could write Dalton's law out. The total pressure in a system is each of its small pressures added together, right? The total pressure is the sum of the partial pressures. These smaller numbers add up to make a bigger number. Now, mathematically, this way of writing things, it's not very commonly used. a mathematician might write Dalton's law out in the simplest possible form here, which says the sigma of all the partial pressures. Now, looking at these two things, even if you've not seen sigma before, what must it mean? Sigma is a math operator that's kind of like a loop in programming. It says, for as many things as there are of this kind, add them up, iterating by 1. So as you go, the iterations are going to increase by 1 until you're out of pressures. So this is the basis of loops in programming. This existed long before programming, obviously. So if you ever see sigma notation, this big E like this, what it means is add up all the parts. Now, I'm not going to sit here and scare you with sigma. If you look at this and you're like, that is Greek. Well, yes, it's literally Greek. But the point of it being is this is easier to write and read once you learn it than this, which is a little messy. But we're going to use this method today. But I wanted you to see this in case you go farther into math or science because, well, we're going to use this more and more in that. At this point, you're probably wondering, Mr. Nedick, why are we still talking about this? This doesn't matter. Well, the air you're breathing right now is pretty important to you. And the air you're breathing right now is a mixture of different gases, right? And the pressure you feel, that 14.7 psi, that 1 atmosphere, that 760 mmHg, right? That pressure is coming from the nitrogen and the oxygen and the argon and the water and the carbon dioxide and the methane and everything else in your atmosphere. But a lot of it is coming from each of these constituents. Let me tell you just how much. So the nitrogen gives off about 78% of the atmosphere. So about 78% of the air you're breathing, and by addition, the pressure on your every square inch of your body is nitrogen. So just knowing that, which of the following numbers is the only one that could possibly be oxygen? So the massive, massive majority, right? 99% of the atmosphere is either oxygen or nitrogen. And almost everything else that's left is argon. It's like 0.09%. The water vapor, the carbon dioxide, everything else, you're talking the hundredths of a percent. Now, this water vapor can occasionally leapfrog the argon and be up to 4% of the overall atmosphere on a really humid summer day. But for the most part, it's actually below argon. So we're going to kind of leave it down here because obviously the relative percentage would change with respect to water. And most chemists will ignore water, but I can't do that. I'm a meteorologist, and, well, water's pretty important to weather. Let me clear my desk for a moment. Since we're talking about constituent gases in the atmosphere, it'd probably be good to talk a little bit more about the atmosphere itself. In grade school, you probably learned about the troposphere and stratosphere and mesosphere. And those are true. Those exist. They're temperature-based differences in our atmosphere. But the neat thing about our atmosphere is 99% or more of it sits below in what's called the homosphere. And that means that the air is evenly mixed. That at the surface, it's 78% nitrogen, 21% oxygen. You go up 100 kilometers, it's still 78% nitrogen, 21% oxygen. That homosphere is really consistent. The very bulk of our atmosphere is consistent. You have to go above that 100-kilometer line, past the Karaman line, and there you start getting disequal mixing, that there'd be different pockets of different gases based on where you go, the heterosphere. Now, the neat thing is the line between the homo and heterosphere has a really cool name. It's called the turbopause, which is it makes me happy as a meteorologist. And the turbopause actually changes its height seasonally. Let me show you a graph of that really fast. So now you've got a new $5 word to pull out at some point, which is turbopause. Anyway, let's come back and do some Dalton's law problems. All right, so we're dealing with a mixture of oxygen, carbon dioxide, and nitrogen. And that comes out to 0.97 atm. What is that? Is that a pressure, temperature, volume? So I'd like to know the partial pressure of oxygen, so that's what the question's asking about. If the partial pressure of carbon dioxide is 0.7 and nitrogen is 0.12. So right off the bat, is this number going to be bigger than, less than, or equal to 0.97? So we could solve this problem two different ways. The first thing we could do is we could try to say Dalton's law. Okay, Dalton's law says P equal P1 plus P2 plus P3. So my total pressure is 0.97. And we could replace these like 1s, 2s, and 3s with the different gases. So let's see, oxygen is our X. Our carbon dioxide is 0.12. Our nitrogen looks to be, our carbon dioxide is actually 0.7. And our nitrogen is 0.12. So that's a really easy question to solve for X. 0.97 equals 0.82 plus X. So what does X have to be equal to? Okay, good. So 0.15 atmospheres. Now, I personally solve these problems like a pie chart. I know the whole thing has to equal 0.97. And I've already done 0.7 as carbon dioxide. And I know that I've done 0.12 as nitrogen, so my X has to be whatever's left over to equal it. If drawing a picture makes it easier than doing the algebra, whatever works for you. Now, the bulk of your work tomorrow is going to look like this, right? It's going to be these kinds of problems. But I could make your work a little harder. As you've probably seen, I've been kind of hiding a bigger problem for you. So we have a 250 milliliter sample of oxygen, and we're collecting it over water at this pressure. And I want to know how much the dry gas, the gas of oxygen without the water, and how many moles of gas I have. So this is a two-part question. Now, if I were to do this to you on an online worksheet, I would guide you through step by step. I told you the water at this temperature has this vapor pressure. Now, vapor pressure is a fancy way of saying partial pressure. It's the more common use of the word, at least when you're dealing with water. So right off the bat, the pressure of the dry gas means the pressure of the oxygen without the pressure of the water. Now, the water and the oxygen together is 760. So is the pressure of the dry gas going to be equal to, less than, or greater than 760? So we can set up a simple Dalton's law. Pressure equal P1 plus P2, right? We're going to give a pressure for each one. So each gas. I've got two chemicals, two gases. So my pressure is the pressure of the oxygen and the pressure of the water. I know my total is 760. And I'm looking for the oxygen. So I can solve for that X pretty easily. Now, this gives me the partial pressure of the dry gas. Just a simple subtraction. Again, this is the kind of problem most of what I'm going to ask you tomorrow is. But this question has a trick up its sleeve. It asks how many moles of that gas are present. Which sounds awfully like a job for my friend Puvnert. So, I know the pressure because I just solved for it. So I'm going to feed that 736 mmHg into Puvnert, but there's a problem. What is it? So it's got to be in atmospheres. The volume was given, but there's a problem with it. What's here? Okay, we're solving for moles. R never changes. And our T has to be converted to Kelvin. So will you do that for me really fast? Great. Super easy problem, just like we've been doing. Let's solve for X really fast. And we get our final answer, 0.00990 mole. Okay, now if you look at this and you're like, oh my God, how am I going to do this tomorrow? I'll guide you through step by step. This does look a little scary, but if we just break it down into like, oh yeah, this is just basically a pie chart problem, or this is just a simple Puvnert problem, it won't be too bad, I promise. Let me clear my desk really fast. I know doing problems this way is pretty tedious, so there's some feral cats in my neighborhood and they had kittens, so here you go, kitties. Alright, so kitty time's over. This is a hard problem, and I'm not exactly sure I'm going to ask a problem this hard tomorrow. And if I do, I would guide you through it, and it certainly wouldn't show up on the assessment. That being said, I think it's important that you see it, because this is definitely a high school level problem, and this is what we'd be doing most of the time if we were in class right now. So let's at least run through one actual Dalton's Law problem. We're going to take 250 milliliters of methane at this pressure and a temperature of this, And in a different container, we're mixing these two things. And we have carbon dioxide at that statement. 125 mils. Is that a pressure, temperature, or volume really fast? So we have these two different things, and we're going to pump them together into a new, smaller flask. It's going to stabilize to a new temperature, and I want to know its pressure. So this is a pretty involved question. Let's do some color coding. Let's make methane green for now. And let's make carbon dioxide blue. What we really need to do is use puvnert 3 times. So first let's start with the green. Let's find the moles of methane. Alright, so I'm going to solve PVNRT. MMHG is going to go to atmospheres. Now 760 mmHg is 1 atmosphere. 250 milliliters. Can you make that liters for me? So over here we have our methane. And we need to set up puvnert again for the carbon dioxide. Alright, so we need to solve both of these equations for x. And onto this guy. Now, we've solved both of these puvnert questions. But what we're going to do is all of this stuff that already existed no longer matters. We're just pumping it. So I want you to think about, like, we have like a little tank, methane, and one of carbon dioxide too. And we put a little pump here. And we pump them into a new container. And this new container, well, it has certain known characteristics. For instance, we know it's 100 milliliters, or 0.1 liters. We know it's at 293 Kelvin, 20 degrees centigrade, right? And we know it has all of these moles in it. So the moles have to be 0.18 plus 0.0095. Now, technically the sig figs here get a little messy, but that's okay. We'll get there. And the question asks for pressure. Well, we can solve that because we know T, V, R, N. P is the only unknown. That's just another puvnert question. So let's knock that out. PV equals nRT. If you get the idea that Dalton's law is often a lot of puvnert, you're right. As maybe you can tell, I made a mistake the first time I did this math because I dropped a 0 here. Anyway, it comes up to an atmospheric pressure of 45.7. So pretty high pressure situation, but that makes some sense. This is a small tank and we're combining more gases into it. So it makes sense that it's significantly higher than any other pressure we've encountered up in the problem stating. Now, if this is daunting, if you look at this, shows like, I have no idea how to do this. Again, if I'd asked you to do just this puvnert, you'd be fine. Or just this puvnert, you'd be fine. Or even just this puvnert, you'd be fine. What I really want you to see, and the trick here, is that what we're doing is adding the moles together. And if you say, oh, all I have to do is add the moles together, then you've gotten the big point of today. Because the ideal gas law doesn't care what kind of gas you have for its moles. It just wants moles. Now, again, if this is daunting to you, okay, I'll guide you through this kind of problem tomorrow. Don't fret too much. But for now, you have no new homework tonight. And until tomorrow, buen camino en todo.